feature distribution, it is by doing something like or applying something like z-score. So or computing the z-score. So computing the z-score, we will do nothing except mapping the values from a particular range to another range. That's it. So for example, if the values in the population count feature that I just mentioned is between, let's say, 500,000 to 1 billion, we will maintain the same range, we will maintain the same distribution, but we will map it to be between maybe 0 and 10. So it is the same distribution, but we will map the values. What does it mean, map the values? Just apply a simple equation to convert all the population count for all countries, like I said, from millions to fit within a particular range between 0 and 10. And this is called standardizing. And sometimes, some algorithms in machine learning in general, sometimes they look for standardized data or standardized distribution. This is how you make it, which is, apply something like z-score or compute something like z-score. The idea of standardizing a distribution means performing linear transformation. So see, linear transformation, which means, like I said, if the data ranges from, if your original range between, let's say, 0.5 million to 1 billion, you are doing linear transformation, okay, to make it between 0 maybe and 10. Imagine it is the same, but why they call it linear? Because there's no change in the distribution, okay, which means if the data originally, this data, the distribution looks like, let's say, this way, 0 to 10 should look like the same, but in a smaller range. Instead of having values between 0.5 to 1 billion, it will have values between 0 to 10, and that's it. So the new distribution, when we apply z-score, the new distribution will have mean of 0, the average will be 0, and the standard deviation value will be 1. So if we compute the standard deviation value for the newly transformed values will be 1. Why this is important? There are some cases, again, there are some cases, sometimes some machine learning models require standardized data, does not require the original data. Other than this, there's sometimes a case where you want to compare values, okay, that came from different scales. A particular example, think about it. If you have, let's say, a data set collected about, North American students, and it has their heights, for example, and their heights in inches. But this is what we have right now about North American students. Suppose we found another data set that's about, for example, University of Houston, and the data about the student height are reported in centimeters. So how to compare, centimeters with inches? You may say, okay, why not to, convert the unit? Yes, you can convert the unit, but the other issue is not just converting make the unit conversion. Is also you need same range between 0 and 10 and 0 and 10. So if you are able to map the values from North American to be from 0 to 10, and then you are able to map the values of University of Houston to make it between 0 and 10, then I can put these two distributions next to each other and I can take a look better to them because they have the same range of values, 0 to 10 and 0 to 10. So that's simply what the z-score could help you to do with the data. Again, it's called linear transformation because the actual relative distances between points before and after transformations same. And to show you this you can see here, this is the original data, the parent heights in inches, and you can see after scaling using z-score, see the distribution, how it looks like. It is the same distribution. Somebody may say, okay, I lost this column here, which is 1, 2, 3, this. Oh no, we didn't lose anything. I'm sorry. This is not just a gap, but this is how the data is mapped. Think 1, 2, 3, see? 1, 2, 3, 1, 2, 3. So we have 10 of them. 1, 2, 3, 1, 2, 3, 1, 2, 3. So this one get mapped maybe to one of these because you can see the difference. This one is big, higher. It gets broken maybe into two pieces. But you can see the distribution looks the same. See, this is a scale. This is between -2 or -3 to 3. The original value is between 64 to 72. So that's why they call it linear transformation. It does not change the distribution. It just changed the values to make it smaller and more readable. More readable. The equation for this is very straightforward. It is, you know, uh, 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 you subtract the value that you want to scale, transform, sorry, which is x, minus the mean, and divide it by the standard deviation. You divide it by the standard deviation of the whole of the original data set. So you need to do two steps here. You compute the mean, the original mean, or the mean of the original data set. You compute the standard deviation of the original data set, and simply start plugging, every single value in your data in this equation. Replace it by x. Replace it by x. Very straightforward example or application for the z-score. So that's for z-score. That's for z-score. There's plenty of examples you can think of. I mean, it's, let me just, it's not very complicated, but you can think about it this way. Suppose you have values. I don't want to spend too much time on it, but suppose you have values, let's say, I don't know, feature, let's say, called h. And that h has values like 2, 3, and 1, whatever. What you need to do is, or and 7, let's say. So first thing, you need to compute the mean, which is u, this one. You compute the mean, then you get the standard deviation for this data set. You compute the standard deviation, which is either, if it's an Excel or Python, it's very straightforward in Excel stdv. You compute the standard deviation, so you replace the mean here, you put the standard deviation here, and you start, feeding these values one by one. 2 minus the mean divided by standard deviation that I computed. Then 3 minus the mean divided by standard deviation. 1 minus the mean divided by standard deviation. 7 minus the mean divided by standard deviation. And that's it. So that's how you compute the z-score. In a separate, continuing with z-score, sometimes you might get a questions like this. What is the probability of observing height 75 or greater from a normal distribution having mean like this and a standard deviation with this value? So this is the mean of the data already given to us. This is the standard deviation already given to us. And the question is, what is the probability of observing a person height of 75-inch or greater, okay, of a normal distribution? Imagine that we assume that the data is normally distributed, which means it has the bell shape. And then we are asking this question: what is the probability? Because now, why we are asking about the probability in this case? We are asking because we don't have accessibility maybe to the whole data set. But what we know about the data set, we know that this is the mean of the data set, or that feature, or the height feature. This is the standard deviation of the person height feature. Okay, but we don't know the whole data set. Otherwise, we could compute the probability easy. But because we don't know, we assume we don't know, or we didn't have access, just we know the summary about the data. So how we know the probability of observing, a height of 75 or greater from normal distribution, for having a population that has the mean 68.31 and the standard deviation 1.79. Simply what you do is you compute you start step one by computing the z-score. So the z-score is 75. You see it, you take the 75 minus 68, which is the mean, divided by the standard deviation, as we saw in the before. This is what you get, this value. Okay, this is what you get. So this is what we call, the raw score of 75 is 3 point, this is how we read it, 3.74 standard deviations above the mean, above the mean. Why we say above the mean? Because it's positive. Okay, above the mean because it's positive. And then, fine, we know that that's this right now. So we know that 3.74. Then step two, there is what's called, cumulative distribution function, or CDF, represented in R by a function called P norm. So this is P norm is gonna compute for us the CDF. So CDF, what does gonna compute for us? CDF, which is this one, CDF, this, read this note, gives you the probability of getting a value less than or equal to a given value. So if I say a P norm 3.74, this will give us the probability of getting a value under or less than 3.74. But the question is asking about what? A greater. So I should apply what? 1 minus P norm. This will give me the probability of getting a value less than 3.74, okay? Or less than or equal. But actually the question is asking about a greater. So I should add 1 minus the probability of getting less than or equal 3.74. So if you run this function in R, you'll get a number, and then one minus that number. This will be the probability of getting a value or observing a height of 75 or greater from a normally distributed feature. Just practice it, run it in R, and you'll see, such a probability. It's very straightforward, but you have to know. I know you may not seen maybe before the CDF. CDF actually is, like I said, it's a function, gives you the probability of getting a value less than or equal to a given value. So this is kind of, as a data analyst, this is kind of a similar questions you might get sometimes, um, as part of the analysis you are doing. They might ask you, what the probability of seeing a female in a state of whatever, playing particular, uh, yeah, musical instrument. Maybe what is the probability of seeing, for example, a young man whose age between maybe range between age A to age Z, in a state of whatever, in that particular month of the year. Could be, for example, what is the probability of seeing or selling a particular product with that much of a quantity in that particular season. So you might get these questions. But like I said, if you have access to the whole data set, you might be able to answer these questions by counting and dividing, counting how many sales they have divided by the total. This is how you get the probability. But if you don't have access to the whole population, and you know only the mean and the standard deviation of that population, this is how you can get answer to such a question. Okay, how you get answer to such a question. The next topic is about correlation. I know most of you just, I'm talking about myself as well. When I want to get the correlation between, two variables, and to see, how they are trending. For example, correlation means if there is very simple example, if the by inheritance, if the parent is tall, we are expecting the child to be tall, right? So if this is gonna happen for sure in a particular family, then we say, okay, there's a positive correlation because the father is, let's say, tall and the son will be tall. So if we find, a data set that shows this relationship, this is something we call it, uh, a positive correlation, because if this is increasing, the other factor or the other feature is increasing. There is sometimes some cases, if something is increasing, other thing is decreasing. For example, if your expenses are increasing, then your saving is decreasing. So this is called negative relationship. This is called negative relationship. But actually, in R or Python, it is simply you run a function called COR, which is, I think it's here. In R, you just write COR and you will get the result. But you need to understand that, in the back end, the correlation is coming from an equation. It's not just that function. Actually, that function is nothing but an implementation to this equation. Okay, and we can read here, like I said, x hat and y hat is these are the mean of x. This is the mean of y. Second variable. Suppose you want to study the relationship between a parent height and child height. X bar, sorry, bar, not hat. X bar could be the parent height average, and Y hat could be the child height average or the mean. Okay, and then these values are nothing but the actual values of every child in the set and every parent in the set. And if you do the calculations or if you do some math here, you will end up having, you know, uh, covariance, which is the equation of the covariance. This is it's nothing but the equation of the covariance of x and y, and divided by the standard deviation of x and the standard deviation of y. So these two multiply by each other. So this is how the equation, ends up looking at. How you end up looking at the equation, as covariance divided by the multiplication of the standard deviation of variable x and variable y. So the question is I want you to understand, that the covariance, what is the covariance, and why we are dividing by the standard deviation. Covariances are scale dependent, okay, which means a large covariance may result in part due to variabilities in x and y. Think about it, if you have, big values or great values, or, height or high values in x and high or or big values in y, this, when you subtract the mean from these values, you will see that this is going to create, big number multiplied by big number, which will inflate the covariance, right? Which will inflate the covariance, make it big number. Okay. um, what does this mean? In other words, this means that the covariance, okay, is impacted by the units. So imagine the case if x in centimeter and y in centimeter, and the difference here sometimes, between the parent height and the child, the mean of the parents is, let's say, maybe 70 multiplied by 70, something like this, will be 1400. So why we are getting this big number from the multiplication? Because both sides are big numbers. Again, x, think about x as an example as the parent height, y is the child height. When we talk about x bar, mean the average or the mean of the parent height, all the parents' height, and y is the average of all child's height, and then xy and yi is the individual, value for height for each child, for each parent, individual for each child. If you are getting big number here, multiply by big number, this will inflate the covariance. Okay, and so we know that. Now there is, because this could cause to look at the equation. So multiplying, then adding, summation. So multiplying big numbers and then adding these numbers, numbers and numbers. Okay. And as we know, covariance measure the degree to which two variables change together. Okay. To which two variables change together. So, a positive covariance means, there's one variable increases, the other one tend to increase. If a negative covariance means if one variable decrease, increase, sorry, the other one decrease. It's opposite relationship. Okay. And as just keep in mind, large covariance does not mean, that there's a strong relationship between these two variables. It could simply due to the variables having large scales, as I mentioned before. If there is a big number here, multiplied by big number will cause the covariance to be a big number. Now, since we are talking about big numbers and big numbers and big numbers, we need to standardize the covariance. As we spoke before with z-score, is we want to bring it down to a range that's readable and make it easy to compare with, you know, a, kind of a general way or standardized way of comparing covariance, in any data set with different data ranges. So that's why they are dividing this by the product or the multiplication of, the standard deviation for the variable x and the variable y. This will bring this covariance, which is the correlation, to be between 0 and 1. And now this will bring us back to the correlation. If you have done correlation before in your machine, or if you run a correlation equation with it, or calculated correlation before, correlation, all the time has values between -1 and 1. So by doing this standardization, the correlation score or correlation coefficients will never exceed 1 and will never go below -1. -1, if we are getting negative values, means we have negative correlation, which means, one variable increases, the other one decreases. If we are getting values positive correlation, which means we have, positive correlation. Positive correlation means, one variable increase, the other one increase. And this is an example of a positive correlation. As x increases, y increases. This is how they look like visually. In negative correlation, one value increases, x increases, y decreases, or opposite. So that's called, negative correlation. Such a situation, if we can see it, inspected visually like this, where we have the data everywhere, this could be no correlation. There might be a correlation. You might see a correlation like 0.3. 0.3 means nothing. It's weak correlation. Okay, because looks, you may say, okay, this looks like increasing. Yes, but you see that's how it is distributed around the mean. This mean, it has weak correlation, and having weak correlation, whether positive weak correlation or negative weak correlation, still means weak correlation. So we cannot make any strong inference that says, or a strong conclusion, to build on. Okay, so we just say, okay, there is no correlation. There is no impact from this variable on the other variable. And in R, there is a function. I think I skipped something. Yeah, if there is, I forgot. Yeah, if R, which is the correlation score, if the correlation coefficient, or yeah, which we refer to by R, if the correlation coefficient, equal to 0, means there is no linear relationship at all, because positive correlation means there is a that goes positively, as one increase, the other one increase. Negative correlation means there is a negative correlation. Yes, one increase, the other one decrease, but still linear relationship. If there is no correlation or weak correlation, the values tend to be close to 0, and having a 0 means there is absolutely no linear relationship. Here we see there's some linear relationship. From this plot, I can tell it might have a weak, for sure it has weak correlation, weak positive correlation. In general, the method that's used for correlation is called Pearson correlation, and I think I skipped something here. It's called Pearson product moment correlation, or sometimes for short they call Pearson's correlation for short. And this is only can be used when we have two continuous variables. Keep in mind, two continuous variables. I cannot use it with categorical variables like female and male variables, or country, or I don't know, age group. I cannot use it. Only if the variables x and y are uh,
in a linear relationship, right?
yes, to inspect if there is a linear relationship, and that's it. but only continuous variables, continuous numbers only. Okay, continuous numbers. But if you have categorical variables, you cannot use it. You cannot use it. For example, you cannot check the relationship between, you cannot use coefficient to check if there is a linear relationship between, let's say, the gender and the age of the students. You cannot do that. Why? Because one of them is categorical. Okay. This is an example for, you can see here, if I plot the points between, I mean, the data points between parent and child, and like I said, I mean, back again to the name, which is Pearson correlation. You know, it's by default Pearson correlation. If you mention it explicitly, still Pearson correlation. So by default, you know, see, by default, these are the same commands, whether you write it or no, it's by default Pearson correlation. And some cases, you know, 0.45, this is the exact number. This is the exact number from running this correlation between parent and child. Because 0.45 is still weak correlation. You cannot come up with any conclusion. Okay, take a look here. You can see, for example, parent with height 71 looks like something like this. Still, the child is 62, right? See, where the same parent who has 71 has a height of 74 or close to 74. So you can tell, you know, the wide range of the values here, the wide range of the X values, the wide range of Y values that correspond to the similar, to the same X values will give you an indication that the correlation is weak. But all the time, you know, beside have inspecting this visually, also try to compute and get come up with a number so you can better evaluate the correlation score. In terms of evaluating the correlation score, you know, this is how you do it in R. If you write correlation to test, for, I mean, sorry, you can run what's called correlation to test, and you can check, I mean, the numbers that's coming out from the correlation, and you can see, you know, try to read them. For example, you see, we said here the value is 45, but I want to test, you know, is this a significant value or no? Take a look here, you know, how to read it. So this is what I wrote here is how you read it, you know. What p-value less than this number that's mentioned here, it is, what does it mean? It means, you know, it is the probability of observing a sample correlation such as this 0.45 under the assumption of the null hypothesis. What is the null hypothesis? The null hypothesis says that true correlation in the population is equal to zero, is equal to zero. And because p value is less than this number, which is less than a conventional levels, you know, we use 0.05 as a you know, this number, oops, as you see this number p value here, it's, see, it's to the power of negative 16. So this is like, you know, 0.0000 something like this. Then to you know, then 22 2 will become in that side. So it's very small number. So because this p value is less than one of these, you know, standard or conventional levels in general, these levels we use them to evaluate the p value. Because this value of p value is less than these ones. Okay, I mean, usually we use this one. We could use this in some cases, but if we compare this number to this number, this one, the 0.05 is greater than this number. So we reject what's called the null hypothesis. Okay. And the null hypothesis, again, it says the true correlation in the population equal to zero. This is telling us, you know, that the correlation is not equal to zero. And the proof to it is the this score. This score. So correlation to test, it just gives you some confidence, okay, that some confidence that the correlation that you computed, you know, is correct. So so when you do correlation to test, the test assume that the correlation between parent and child is equal to 0. But when you get a value like this, and then you look at p-value is less than, this value is less than 0.05, you reject the null hypothesis, which means you accept that the correlation is 0.45. This is a statistical way of doing things, or reading things. But actually, I mean, if you take a look again, you compute this, you get 0.45. There's a way of doing things. Other So we are done with the correlation, which is a correlation between two variables. We spoke about z-score. We spoke about the probability. Let's talk about, testing the mean differences. Testing the mean differences here. See, if you have the whole population, a data set about the whole population, okay, you can just simply get the average, and what is the mean of that population. The average, for example, if you know if you are collecting data from North American students, all the child's or all the students' heights, you have access to the whole data set. If I ask you what is the average, you simply calculate the average. But if if I have sample of the data, I have sample only of the data, not the whole data set. These cases, when we have sample, when we deal with sample of the data set, of the data, okay. If we have sample of the data, okay, and I want to test if that sample of the data, okay, has a particular mean or no, okay. So I can simply do what's called t-test for one sample, t-test for one sample. And in this case, t-test, you feed the data. So this is the data 105, 95. These are values for a feature called IQ. I don't know what's IQ. So these are the values. And I want to test if the mean, mu is the mean, the average. If the average of these values are equal or close to 100, is there a strong support that the average or the mean is close to 100 or no? Okay, so when you run this test, you'll get these values. You get this 102, which is the average. Mean of x is this one, 102.6. So the average of these values, if you do calculate them manually, you will get 102.6. But let's take a look to the p-value. So p-value is 0.3892, which is greater than 0.05, the one we used before. So see, p-value is relatively larger than 0.05. So we fail to reject the null hypothesis, and therefore we do not have an evidence that the true mean is not equal to 100. We don't have an evidence that the true mean is not equal to 100, because we can see it. The mean is 102.6, right? But we use p-value is just kind of to give us some confidence, to give us some confidence. There is what's called two-sample t-test, where you have a list of values. You want to compare two samples. This is sample one, this is sample two, and you want to see if they are different, if their means are equal or no. You want to see if their means are equal to or no. In one sample, you try to see if the mean of this equal to a given mean. In the two sample, you try to compare the means of two sets. So this is a grade, for example, might be first exam grades, and you want to see if the students, the performance of the students in exam one and exam two is close to each other. Okay, so we perform what's called t-test. Okay, t the test for two samples, and by default it will implement, what's called, or execute what's called Welch two-sample t-test. So see, this is a statistical method. You can read about it by itself. And at the end, if we will get a mean of x, a mean of the first one, which is x, they call it x, is 37.4. The mean of the second sample is this, 1.3. And we can see p-value is 0.004, which is less than the 0.05. Okay, so see, R conducts which is an adjustment for inequality of variances, and the mean we can see, the true mean difference, between these two, and let's see, it's failing between these two limits, and this is telling us because of the p-value is less than 1, you can see there's a true difference. There's a true difference in the mean. Okay, there's a true difference in the mean because p-value is less than the the value we know, which is 0.005. So this is called t-test, and there is another one called p-test. And again, these two tests work with sample. If you have the whole population, you just calculate the mean for the population and the mean for the other population and just compare them. If you know the sample, the whole population here, you can just calculate the mean for that column or that feature and compare it to that any given value right away without going through t-test and looking at p values. So these kind of two tests, please read about them, see how you implement them in R. Read more, find examples about them in addition to what we have seen in the class. But these kind of different things that you can do in data analysis, these are sample of different techniques or statistical techniques that you can work with in the data. I don't want you to apply just, for example, correlation. I want you to learn a little bit about the background of correlation that's based on the covariance, okay, which is the relationship, which is nothing but a relationship that show you the how how two variables can change together. And we inspected the covariance. I want you to be able to analyze the covariance with confidence, and you explain it well, that correlation is about knowing or learning if there's a linear relationship between these two variables or no. So now we are down to 15 minutes or 14 minutes. I want to show you talk about the other piece with you. So I want you to start looking at SQL. So this is this is Geeks for Geeks. It's one of the good websites. This one, yeah. So there's multiple things we want to learn in this data analysis class about SQL. So you see these ones. Let's forget installation. But let's focus on the commands. So we need to be able to create. I want you to be able to create database. However, if you work as a data analyst in a company, they will not let you create a database. Why? Because there is what's called database administrator who create databases. So we have commands, but I want you to learn these commands. How to create a database, how to select data from the database, how to insert into a table, how to update a table, how to delete from a table, how to alter a table, which means you add features or fields to the table or columns, and so on. There is some basic queries we do all the time, which is select distinct. You will know what is it. Order or filter sort the results. Select multiple records. Search using like, use logical operators, comparison operator, between and in to select based on range, and so on. So these are really good topics that we will cover in this. And there's you can see here some data cleaning and transformations for data science. You can see string functions. See, help you to join two values together. See, get you the length. See, this is kind of a processing. You are doing some processing in the top of the in the top of the on the data. So which is what, data cleaning and transformation, and this is actually feeds to the to this class objective, which is to help you learn more of the data analysis skills. Definitely will not be able to finish everything. We will try to do go over I will not be able to go over it, by myself. I mean, and during one class, but we'll see what we can cover. But importantly, I will share this link with you, and you are required to go over this part until aggregate function and joining from multiple tables, and then if you can reach that point, that's fine. And then I will talk about this part in the class only this part I will cover in the class. I may spend maybe 15 minutes going over some of these topics before, but in a class, but then the rest of the class will be about this part, which is the data cleaning and transformation for data science. And we'll go over the website itself. I will not prepare slides because it has already some examples that we can use to explain what we want to do. So I will share this link with you, um, and I will not post a home. I will post a homework about. I will let you know about what, but I'm thinking only about this part only, and then the second part, which is this and this and this, and the data science will be after the next class. So the other homework will be so. But yeah, it will not be fully covered. I will share the instructions later. But I want you to know, I want you to do some self-reading about this, uh, to be able to interact with these commands. Okay, you may say, okay, what I should use. So there is here, it's teaching you how to install MySQL, which is open source, which means does not need license. You don't need to spend money on it. So you can install MySQL if you have Windows machine. If you have Linux, I think the same for Mac you can find to install. And yeah, so these are the steps. Just go over them, download the installation, work with it, install it. If you have access, Microsoft Access, people underestimate Microsoft Access, but let me um, just find. I didn't use it since years, but I can show you. Let me create a table of. Get stuck. What happened? Okay. I need to go to design view. Let's create ID number and then first name table as first name, and then last name, and then maybe when you create a database, it's important to define the data type. So for example, first name, last name, age shouldn't be short text, should be something like number. ID, this is auto number, which means will be incrementally, but I don't like this. I want to have it as number. And we need to add what's called the primary key. See this key, little key next to ID. You can have it whatever you want. I want this, for example, to be primary key. So primary key is one of the concepts in the database, which means, I want, like your ID in the university. If there is no two students that they have the same student ID. So that's why it's important to identify the records or differentiate the records that you have in any table using the ID. So primary ID. Let's do this. And then let's open this. See, let's add some records. Let's say, just for sake of simplicity, Sam, age 12. Let's give it a number 14, ID 14. Let's call Alex, age 35, 20. I don't know, Mike, age 36, something, or let's put it 80, something like this. So that's for the table. So we created the table in Access. Let me double check other things. So we need to go to queries. Okay, let's see if we can run some queries. Yeah, query design. So this is a query design, and there should be a query where we can write some. What is the queries actually? Out from the query, create. There's a way where you can write. Okay, so let's do a query here. It's a field ID. Oh, we need to bring table one. Then we can select, let's say, search by age. We want the age to be greater than, I think, 20. think it should work, and then run this query. Yeah. So this is a query. I'm asking if there is an age greater than 20, but not this is what I'm looking for. Oh yeah, SQL view. Okay, that's SQL. That's a query. That's the thing I'm looking for. I think you can also run some. So see this query, for example, I said select age. Okay, select age, or I can say select star. Select star means select all the columns in the table where all the columns from which table? Table 1. What is the condition I want? I need only age, all the record that has age greater than 20. If you take a look here, you know, this is the age. Greater than 20, we have Alex and Mike. So if I go back to the query, which is somewhere here. If I run this query, I don't know how to run this, but let me see. Should be SQL. I totally forget. But oops. Let's go back to this. Let's see. Yeah, now we can see all the records. So before, if you remember, we saw only 8. Yeah, it's just changed the view look like. So if I change this to be table 1 dot age, you will see only one column in the output. Let's see, view or run. Yeah, so one column, which is the age. But if you go to SQL and then say star, which means all the fields, then I click run, I can see all of them. See ID of name. So this is Mike and Alex, their age greater than 35. So that's called SQL. So you can run SQL commands in Access. So if you couldn't install that one, I'm not sure about the rest of the commands. So if you don't, why I'm bringing Access, because you need to work with MySQL and Postgres. If you have difficulty with these, you know, we can still, I think, implement some of these. I don't know about insert, honestly. I don't know about update. Update might work. I don't know about insert. Maybe some commands could work in Access, some command may not. So it's your responsibility, you know, if you cannot implement it in Access and you have it in the homework, the way it's either collaborating with other students as a part of the team, or whatever way you want. But Access could be an additional solution to you. And I'm trying to show you here that you can run SQL commands in Access. And you can see all of these are SQL. See, everything is SQL. So that's why, you know, I proposed Access as a second option to you. So this is going to be provided. I'm going to put it in Canvas right now, and we will stop here for today. So this is, yeah, I will let you know what you read from this. I put the instructions in Canvas. Just don't quote me in anything right now. But yeah, we will see it here and under what module 2. I'm going to add external URL and learn SQL, I will call it. And I'm gonna add, I publish it, and I will add a header to this to show you, for example, you know, what you need to read before the next class. Sounds good? Any questions? Okay. If there is no questions, have a good night, everyone, and talk to you in 2 weeks, and wait for your next homework. It will be under module 2. It will be under module 2. So far under module, I will upload the slides, so you'll see the slides under module 2, under study material, and then I will create a homework for you under assignments in under module 2. So wait for that to happen. Okay, in the next 2 days at most. Thank you so much and have a great evening. Bye bye.
Good night, sir. Thank you.
Thank you. Have a good
Thank
night.
you. Bye, sir.
Bye.